So this is my talk. I originally titled it A Complete Guide to C++ Object Lifetimes, but then I figured I better have the insurance in there because it's a lot of material in there. And there's a lot more I could talk about if I had even more time. But don't worry, the talk is going to be organized in levels. So we're going to start with the very basic, and then we go deeper and deeper until we reach the area of open standardization research problems in order to fix fundamental bugs in the specification. So you can stop watching the YouTube video at any time and you won't miss anything out. So after the end of each level, if you're like, you can ask questions pretending if there are critical questions, feel free to ask them in between the talk. If there are more in-depth discussion, we can do that at the end. And also in the early parts, lots of questions are probably going to be deferred to the later levels. But if you're sitting on the very right, I can't see you. If you're in the back, if you have questions, I can't see your hand because of the lights, so just shout or something. So let's begin. So I'm going to talk about object lifetimes, which means the first question is, what are objects and what is lifetime? And objects, here in this context, have nothing to do with object-oriented programming. Objects are fundamental to C++. It's a terminology the C++ standard uses, and essentially everything you do in C++ does something with objects. So this is a quote from the standard. We're going to see those a lot. The constructs in a C++ program create, destroy, refer to, access, and manipulate objects. So all a C++ program does is manipulate objects. And to understand objects, we need to understand three terms: storage, value, and type. So let's begin with storage. So a C++ program has memory, which consists of bytes. It's a sequence of contiguous bytes, and every byte has a unique address. So here's a bit of memory. Like, it's just a bunch of bytes, and these bytes store bits, and the bits have some numbers I've given in there. And for example, we've got the highlighted byte, which has the value OX41. Now, OX41 is just the bit pattern in the byte, but what does it mean, right? What does OX41 mean? It could be the 8-bit integer 65. It could be the ASCII character capital A. It could be the start of the string that begins with capital A, or somewhere in the middle of a string that has a capital A. It could be part of a 32-bit integer, so together with 3 more bytes, it makes up a 32-bit integer. Or it could be anything else, like it could be some enum value, it could be part of a float, whatever. And this is the distinction between the physical bits and the value. So the sort of the Bible of C++, elements of programming, gives a good definition of value. So we've got a datum, which is just a sequence of zeros and 1. And this datum can be our OX41. But on its own, it's meaningless. Only together with some interpretation does it become a value. So a value is an interpretation of a sequence of bits to represent some mathematical thing. Like a value is a mathematical term. It's unchanging, it lives forever, it's a mathematical idea. It's the number 42. And then the datum is like a physical representation of that thing in memory. And now a type simply specifies the interpretation of a datum. So it's essentially a function from datums to their values. So for example, we have the type unsigned char, and it means that we take 1 byte of memory, that's our datum, and interpret it as an 8-bit unsigned integer to get the value. Or we can have the type int, there we take 4 bytes of physical memory and interpret the bits as a 2's complement 32-bit integer. Or we can have more complex types, like string. So then we take 24 bytes, the first 8 bytes are a pointer to a null-terminated string, then we've got size and a capacity. And so we take the physical bits and interpret it according to the rules of a type, and then we get a mathematical value. And now an object has a particular type, occupies a region of storage, and at a particular address where it stores a value. So that's an object. It has a type, it lives somewhere in memory where it stores its value. So here we've got some code. We first create an int object, we call it x, and we give it the value 42. And then we've got the second object, a float object, we give it the value of 3.14, and now we've got 2 objects. They live somewhere in memory, they store some value. And the value of an object can change over time. So for example, we can assign the x a new value, and now x stores the value 11. Unless the object is const, then the value can't change. But in principle, an object has a value at a given point in time, and this could change over time. And like a contrast, the value is just a mathematical thing. A value never changes. Like the number 42 is always going to be 42. It doesn't suddenly change later on. Only an int object can have the value 42 and later on change that. Now, it's important to point out at this point that functions, for example, aren't objects. Functions are their own thing. Even though they can have an address, they're not really objects. Only function pointers are objects. So here we have a function f. This is not an object, this is a function. And then we've got a pointer to f. This is an object, and that value is the address of f. So the object is the thing that can change, that can be assigned, that can be manipulated, and the function is just some piece of code. And similarly, references aren't objects. References are simply aliases to existing objects. So here we're having just one int object, x. And then we've got two names for that, the variable x itself, and then an alias ref. So references on its own, they're just simply aliases. They don't have properties on their own, they just have the properties of the object they reference to. Now, what is lifetime? The lifetime of an object is a runtime property of the object. So an object has a type, an object has an address, an object has a value, and an object also has a lifetime. It's just another property. It's a pretty important property, because all the other properties of an object only apply during its lifetime. If you access an object that is outside its lifetime, it's not alive, you can't do anything, you can't do a lot with it. Like, there are significant restrictions on the use of an object before the lifetime has started and after the lifetime has ended. So it's important to understand when objects are alive in order to write concrete code. So this is a very high-level picture. The object lifetime in a nutshell. The first step is always we allocate storage for our object. We then initialize an object which starts the lifetime. So when an object, so the initialized is in question marks because you don't really need to initialize an object in order to start it, but we'll cover the details later on. But once we have the lifetime, we can use the object. We can change its value, we can read its value, we can do stuff with it. Then at some point, we're going to destroy the object, which ends the lifetime. And at some point, hopefully after that, we're going to deallocate the storage of the object. And this is the high-level picture, and the rest of the talk just going to look at the details. So, important note about terminology. The C++ standard describes that objects can be created. And when an object is created, it just means that we've got the mathematical thing, some object, which has some properties, which we can start to talk about. But it does not necessarily start the lifetime yet. It just means that we now got a thing, an object, we can talk about it, and at some later point, we're going to start the lifetime. However, on the flip side, when an object is destroyed, this is actually a physical operation we can do on the object, which ends the lifetime. So there's a bit of an asymmetry in the terminology here. So create just means we have something we can talk about, and then destroyed actually means we end the lifetime. So destroyed isn't a one-time operation that we actually do. I'm going to try to avoid using create to mean start the lifetime, but like it's the colloquial usage, so I might slip up there. But like technically, it's like a different thing. Like we create an object, which just means it's something we can now start talking about it, and then we can, for example, start the lifetime of it. And also note that lifetime is something the standard invented in order to describe the semantics on a C++ program in the specification. It has absolutely nothing to do with the actual physical machine where your program runs on. Like objects aren't a CPU thing. Objects are a C++ standard thing. And all the standard talks about for lifetime is just in order to describe when a program is valid, when a program is invalid, and so on. So this is very abstract theoretical talk, and we're going to encounter some things which are undefined behavior, but just because the specification is a bit buggy and which aren't really any problems in practice. So with that, let's begin. So, level 0, variable declarations. We're going to see intro.object/paragraph1 a lot, and which is a sentence that describes when objects are created, and one of those places is using a definition. So for example, in this code, we have an int variable definition, which creates an object, also allocates storage for it, and starts its lifetime. We can then use the object, read it, modify it, read it again, and then in the end, it's destroyed. And to understand the details about when exactly we allocate the storage for that object and when we start the lifetime, we have to look at the storage duration of the definition. So the storage duration is another property of an object, and it defines the minimum potential lifetime of the storage containing the object. And it's determined by the construct we use to create that object. So depending on how we got the object, we have different storage duration. And here in this particular case, we are only dealing with static, thread, and automatic storage duration, which is the storage duration of variables. Automatic storage duration is the easiest one. When we've got a variable that's inside the block or parameter scope, and doesn't use any special keywords. It has automatic storage duration. It's created, the storage is allocated when we enter the when we encounter the definition, and when the block exits, we are going to destroy it. So when we start executing a main function and we reach the first line, we allocate storage for A. We then allocate storage for B. We then enter a nested block to allocate storage for C. Then we exit the block, which deallocates storage for C. And then we deallocate A and B when we exit the function. This is automatic storage duration. This is very straightforward. Static storage duration are variables at like namespace global variables. And their storage is allocated when the program starts and deallocated when the program ends. So here we've got a bunch of global variables. They all have static storage duration. And when the program starts up, we allocate storage for them. And when the program terminates, we deallocate storage for them. So throughout the entire lifetime of the program, we've got storage for those. Thread storage duration is similar when a variable is declared with thread local, but instead of having one object throughout the entire program, we're having one per thread, and when the thread starts, we allocate the storage. So here, when we start executing main, we're having one copy of the thread local variable, whose lifetime is going to match whose storage duration matches the storage duration of the main thread. And when we start a second thread, we will allocate a second copy of that. And this lifetime will then only last as long as the storage duration only lasts for the second thread. So when we destroy the second thread, we also deallocate the thread local variable for that thread. And when we exit the main thread, we deallocate the thread local storage for the other variable. Now, in general, the storage duration is not the same as the lifetime of an object. Just because we've got storage for an object doesn't mean the lifetime started yet. The lifetime only starts when we've got storage and we completed the initialization. So when are the variables initialized? Well, for automatic storage duration, when the storage is allocated. So in this case, storage duration and lifetime exactly matches. So when we allocate storage, when we encounter the definition, we also start the lifetime of the object. However, for static and thread storage duration, it's complicated because global variable initialization depends on a lot of factors. We've got function local statics, which are initialized at a different point than global objects outside of a function. We've got const init and dynamic initialization and nifty counters and the module dependency graph and inline variables. I gave an entirely separate talk just about when the global variables are going to be initialized. Because even though the storage exists the entire time, the initialization potentially happens at a different time, and only then does the lifetime start. So there's entirely different talk you can watch after this one if you're interested. But for automatic storage duration, when we've got storage, we start the lifetime and we can start using the object. Now, the initialization is entirely optional, because in general, we can start an object, start the lifetime of it without a known value. So more precise, when we allocate storage for an object and we don't initialize it, then it has an indeterminate value. And it will keep having an indeterminate value until we give it a different one. And when we read something with an indeterminate value, we have undefined behavior. So for example, when we just write int x, this allocates storage, but it doesn't do any initialization, because the default constructor does nothing. So, but it nevertheless starts the lifetime, because we done any initialization we wanted to do at this point, which is just we didn't want to do any initialization, so the lifetime starts, and we have an indeterminate value. This means it's undefined behavior to read the variable, because it doesn't have a known value, but it's not undefined behavior to assign something to it, because even though we didn't do any initialization, we've got an object, this lifetime is started, we can start using it, we just can't read it yet. And then the second read is okay. And now the current quote says the behavior is undefined when we read a value of undetermined value. This is actually going to change in C++26. So in C++26, we're going to introduce erroneous behavior. And erroneous behavior is essentially what undefined behavior should have been in many cases. So with undefined behavior, the compiler can assume that it doesn't happen and optimize accordingly. With erroneous behavior, the compiler can't do that. What the compiler is allowed to do is to issue a diagnostic and terminate the program. So it's sort of a contained version of undefined behavior. And in C++26, read of an indeterminate value is erroneous, not undefined. So the compiler is allowed to catch it dynamically at runtime when it happens, but it's not allowed to optimize based on the existence of reads. So we're going to limit undefined behavior in that area in C++26. that is level 0. Any questions so far about object lifetime? Yes, at the very back. So what's the cost? I'm not prepared to answer that at this time. But yes, it's a trade-off. They're gonna look at that various cases on a case-by-case basis, but yes. Okay. So let's move on to level 1, new and delete. An object is also created by a new expression. So when we have a new expression, we create an object. Then we also need to destroy it using a delete expression. But this is pretty straightforward. So when we write new int, we create an object, we allocate storage for it, we start its lifetime. We can then use that object freely, and then we delete it, we destroy the object, deallocate the storage, and end the lifetime and deallocate the storage. This is pretty straightforward. And just like with regular variables, it's also possible to create one with indeterminate values, right? New int without anything starts the lifetime. Actually, I think that's not true. I think it. No, I think, yeah, it's an indeterminate value. So we can have the undefined behavior when we read it, but when we assign it, it's okay. And that's level 1. It's even easier because we have full control over when the object is allocated, when the lifetime starts, and when it's deallocated. So let's start about something more interesting, temporary objects. An object is created when a temporary object is created, which is a great tautology. So consider this code. We've got a function f, which takes a reference to an int const. And then we're calling it with the number 42. Now, the number 42 is a PR value, right? It doesn't live anywhere in memory. It's the number 42. It doesn't have an address. We can't modify it because it's always going to be 42. But what does the reference bind to? Like, a reference is an alias for an object. So where's the object coming from? And the answer is the compiler has to create a temporary object, give it the value 42, and then have the reference be an alias for that. Because a reference can't bind directly to a value. A reference is an alias for an object. And we need an object in order for a reference to make sense. The technical term for this is temporary materialization conversion, which is a great phrase for Hangman. And the description reads like somebody was desperately trying to hit a word count. So when we've got a PR value of type T, which is this number 42, for example, it can be converted to an X value of type 2, which is just an R value reference to T. This conversion initializes a temporary object of type T from the PR value by evaluating the PR value with the temporary object as the result object and produces an X value denoting the temporary object. Makes sense, right? But what it essentially says, we've got a PR value. We need an object. So we will create an object, give it the value of the PR value, and use it. And this happens every time where we use a PR value, but we actually wanted an X value. For example, we want to bind a reference to a PR value, like in our previous case. This has to be an R value reference or a const L value reference, because a non-const L value reference doesn't bind to a number 42, right? You can't have an int ref equals 11 on most compilers. Also, when you want to do member access on a PR value. So you've got a function that returns a std string by value. This is a PR value, and then you want to call .size. .size gets this pointer. So we need an address of something. So we need to create a temporary object, initialize it from the PR value in order to use it. Also, when we use arrays, because arrays really want to be pointers. So whenever we use an array, we will create a temporary object. And interestingly, when we discard the result of a function that returns a PR value. So a function that returns a std string by PR value. This is just a value. But we want to run the destructor when we destroy it. But in order to run the destructor, we first need to create an object in order to run the destructor. So when we just call a function that returns a PR value and ignore the result, we will create a temporary. Now, what about the lifetime of this temporary? Creation is easy. When we create the temporary, the lifetime starts immediately. And the temporary is then destroyed at the last step of the full expression that contains it. So here we've got a function f, which takes a bunch of references to force creation of temporaries, and then we call it with 11 and a PR value with return from G. This creates two temporary objects whose lifetime starts immediately. Then we evaluate the call of the function f, and once we're done and control flow reaches the semicolon, we destroy those temporaries. And this means that while we're inside f, we can freely use the reference, right? Because the reference will point to the temporaries that will outlive the calls of the function. While we're inside f, if we take the address of those and store them somewhere else and use them later on, we're accessing memory that has been destroyed, right? Because we destroy them after the call. Also, when we return a reference to them, this can be problematic. Now, there are two exceptions to this rule. This is called temporary lifetime extension. The first one happens when we have a reference that is bound to a temporary directly. The lifetime of the temporary lives as long as the reference. So the first line creates a temporary object initialized with epoch42. And then the reference is available throughout the rest of the function. So the lifetime of the temporary gets extended to match that of the reference. So the second line is OK, because the temporary is only destroyed when we no longer can use the reference. Which is, in principle, nice, right? That the compiler does that for you. But you have to be really, really careful with that, because the rule only triggers when a reference is bound directly to a temporary. It doesn't trigger when we've got a reference to a temporary. So consider this code. We've got getStrings returns a vector of strings. And then we call it and bind it to a reference. Here we trigger temporary lifetime extension because we bind the reference strings to a temporary object whose lifetime is going to match that of the strings variable. So this is good. But then the second line, we're binding it to the result of calling operator square bracket 0. Now this will also create a temporary object in order to call the member function. But the call operator, the subscript operator, returns a reference. So we're not binding a reference to a temporary. We're binding a reference to another reference to something that lives as part of the temporary object. So temporary lifetime extension doesn't kick in because we're not binding a reference to a temporary. So when we reach the semicolon, we're destroying the vector of strings, and we just got a reference that immediately dangles in the second one. So you have to be really, really careful when using temporary lifetime extension. The second case is when we've got temporaries created within the range expression of a for loop. So everything after the colon, all temporaries created in there are going to live as long as the for loop lives. So in this case, we are iterating over all the strings returned from getStrings. This is also going to create a temporary object, and that temporary object that holds our strings is destroyed when we are done with the loop. So everything inside the loop can safely access it. Similarly, we can iterate over the first string, because the vector of strings is a temporary object, but then temporary object is only destroyed when we're done with the loop. So this code is also safe, because there's a special exception to the special exception for range-based for loop. And this was only added in cplusplus23, I believe. So before that, the first one would work based on the previous rule, but the second one is just immediately dangling. But since cplusplus23, both of those are completely fine. You can safely just use the range-based for loop whenever. Don't have to worry about it at all. Just forget what I told you, and you can just write this code.
Thanks, Nico.
Yeah, thanks to Nico for that. Any questions about temporaries? Yes?
All right, so I'm aware that this is like going to be really...
Sorry, there's a microphone coming if it's a long question.
Yeah, so I'm aware like this is going to be a bit cursed, but so now we had like a function returning a value and bind it to a reference. But what if we like changed getStrings to return a reference to state vector, and then do like return vector like constructed in the return statement? How long would that then live? Like I'm not wanting to do that, but out of interest.
Yes. So you've got our getStrings function returns a const reference to a vector of strings, and we write return temporary vector. This will just immediately dangle, because the temporary will live until we reach the semicolon of the return statement, not of the semicolon on the caller. And I think there is some proposal to even disallow that, because this is just stupid to do. But yes. In general, just like temporary lifetime extension, like for the range-based for loop, is nice, because it's not obvious that we're creating temporaries. But in all other situations, just forget that temporary lifetime extension is a thing, and you're going to be so much happier. There's going to be a lot of that coming up in the talk. So there's a lot of details, but the details shouldn't really matter for your life at all, I hope. So let's talk about placement new. Now, an object is created by new expression, but there's a special kind of new expression. The so-called placement new expression, which doesn't allocate any memory, it just explicitly calls a constructor. So we've got some memory from somewhere. And then we can use placement new to explicitly create an object in that memory. So here we are explicitly creating an int object in our memory and getting a pointer to it. So we manually create an object, essentially. So placement new is the way to manually create an object, start its lifetime, and to manually destroy it, we can explicitly call the destructor. So we can write object dot tilde and then the name of the type, and this explicitly calls the destructor. And this is necessary when you use placement new, because we've manually created it, we also manually need to destroy it. There is some syntax quirk about this. So the type name there in the destructor call can only be a single identifier. So it can't be like int, because int is a keyword. So you can't write x.tilde int. It also can't be a qualified name. So you can't write x.tilde std string, just because the grammar doesn't allow it. You can still call the constructor using like a type def or using declaration. The grammar doesn't allow it. So I will just use the standard library function destroy_it, which just calls the destructor. And because in this case the type name is always t, like the grammar allows it, and we can always write it regardless of what the type is. This is just a purely syntactic quirk of the language. So destroy_it explicitly calls the destructor. So in order to call placement new, we need some memory for our object to live in. So how do we get that memory without having actually created an object, right? How do we get that memory? And we can use it with malloc, for example, right? The C function malloc, it just allocates memory, it doesn't create any objects. So we get a memory, we call placement new to start the lifetime of a new int object in that memory, and then we can happily use it. Right? So we can start using it, and then to end the lifetime we need to destroy it, and then we also need to free the memory. And this is the full life cycle of the object, just like manually written out every single thing. A more C++ version uses operator new. So unlike new, operator new just allocates memory and doesn't actually create any objects. So essentially the code looks the same with malloc. We just use operator new, and then to destroy it we use operator delete. We can also use an array of unsigned chars.byte. So here we've got an unsigned char array that is aligned for an int and big enough for an int. So this can provide storage for an int object. So we can then use placement new to create an int object in that buffer and start using it. And two things to point out about placement new. Placement new can be overloaded to do whatever you want. So if you want to be really careful about that, you always have to use the colons in front to call the global version, and also have to cast the pointer to void. Because a user can provide like a placement new that takes a pointer to unsigned char and does something entirely different than the version you actually want to call. So to be like entirely correct, you always have to use the colons and the static cast of void star when you call placement new. C++ is just a great language. So now we've got our int object, and then as before, we can start using it. We need to destroy it, and then the storage gets deallocated automatically for us because it's an automatic variable. Now the interesting thing is this one. We can also reuse the memory of an existing object. So here we got our int. We then destroy it. Now we don't have an int anymore. We just have some space where an int object used to live. We can then use placement new to create a new int object in there. And then we can just use that. And then when the int gets destroyed, the lifetime ends. Now, there is something interesting about the final semicolon, which ends the lifetime. Can anybody see what it is? Okay. So, yes? Sorry? Yeah, so the semicolon, it destroys the int object of the automatic variable of the first line, right? But that one doesn't exist anymore. We've created a new one in it. So is this a problem? I'll get back to that. But in principle, we can reuse the memory. But we have to be really careful. For example, const is still const. We've got our const int. That's 11, and it's const. Now you can't just go out and say, okay, let me just destroy that and create a new one. That is 42. That would change the const value. And that is undefined behavior, because const is still const. Mostly. Because when we've got a const int heap object, that doesn't matter. Then we're allowed to do it. Because for objects on the heap, const doesn't matter. They're never really const. So we can just do that in this case. But when we've got an automatic variable or a static variable, we cannot reuse their memory for a different object, because that would mean that const objects are no longer const. The second thing is to remember, the compiler doesn't care what we're doing and still wants the destructor anyway. So when the destructor has side effects, this can lead to undefined behavior. So here we're having a string, we're destroying that string. That's good. But then the compiler is going to destroy the string again, right? So this is a double free. The compiler doesn't care that we destroyed the object, it's going to destroy it anyway. So when we destroy something with a non-trivial destructor, we have to be sure that we put something in there back before the compiler destroys it again. Otherwise, we have undefined behavior. And then we have to be really careful with this code. So we've got our int, we destroy it, we create a new one, we use the pointer return from placement new. That is good. That is a pointer to a new int object. What about this line? This uses x, but we've destroyed x. X doesn't exist anymore. And similarly, the destructor in the semicolon, when we reach the closing brace, also destroys x. So is this fine? Can we just continue using x as if nothing has happened? Well, the standard says, after the lifetime of an object has ended, and we get a new object at the same location, a pointer that pointed to the original object, a reference that referred to the original object, or the name of the original object, will automatically refer to the new object if the original object is transparently replaceable by the new object. So we can use x, even though we did some change, we used the memory, when we've got transparent replacement. So what does transparent replacement mean? So A and B is transparently replaceable if A and B use the same storage, which makes sense. They have to be on the same location, otherwise it doesn't make sense to talk about it. And A and B have the same type, ignoring top-level CV qualifiers. So we've got our int object, we destroy it, we create a new int object at the same thing. That is fine. That is transparent replacement because there was an int before, there's still an int, we're good. So we can just reuse original names, original pointers, original references as if nothing has happened. There are 3 exceptions, const objects, base classes, and now unique address members. And then when sub-objects, it recursively considers it. But that's it works out. So in this case, it's perfectly fine. Because we have an int object, we destroy it, we create a new one. This is transparent replacement. We can just continue using x. The compiler is also going to destroy x. This is also fine, because x just magically refers to the new object we just created in there. Similarly, this implementation of the assignment operator is also fine. We destroy object, and then we copy construct a new one in space. This is transparent replacement, because we have the same type, we use the same storage. And it's not const. Right? So none of the exceptions apply here, and this is fine. And note that this changed over the course of C++ standardization. The rule used to be more strict. So this is perfectly valid. We're using transparent replacement. And just to consider the case of sub-objects, so here we've got a member function, we destroy our member x, and then we transparently replace it, and everything just works out fine. Now, one of the exceptions was const objects. Regular const objects can't be replaced at all because they're const, but like heap const objects can be. So here we've got a const int object on the heap, which we destroy, and then we placement new a new one in there. This is fine, because it's a heap object, but it's non-transparent. So when we dereference new pointer, which we got from placement new, that is okay. But when we dereference the pointer, that is undefined behavior. Because the pointer points to an object that wasn't transparently replaced by the new one. So the old pointer is invalid, even though it has the same address as the new pointer. You cannot use it anymore. And this is because the compiler sees this code and sees, okay, pointer points to a const object. And we're not going to have it point to something else. So the value of star pointer doesn't change because it's a const object. And so the compiler would like to optimize all star pointer to just be 11, because that's the value it has been. And this placement new destroy would break that optimization, which is why it's undefined behavior to use that pointer again after this placement new. So even though both point to the same address, we can only use the one returned from placement new. Now to fix that, we have to use the function some of you have probably been waiting for, launder. Now, launder is a magic identity function. It takes a pointer and it returns a pointer. And it doesn't change the pointer, but it magically makes it valid again. So we can launder our pointer, which doesn't change anything, but now we can dereference it. Launder essentially tells to the compiler, I know that it points to a const object, but please forget that it pointed to a const object. It may have changed. Please generate code again to reload the object. We're going to explore exactly how launder works later on in the talk. But for now, launder can be used when we're doing non-transparent replacement and you still want to reuse the original thing. Now, launder also helps with references. So similar case, now we're just having a reference to the original object. We're doing a replacement. We're not allowed to use the reference because it refers to an object that has been destroyed. We have to launder the address of the reference, dereference it to get a new thing back. But std launder isn't magic. It doesn't magically prevent undefined behavior. So when we've got code like this, so we're assuming int and float are the same size. We've got a float object in the heap. We destroy it. We placement new an int in there. This is perfectly fine. We've got enough storage. We've static asserted it. But it's non-transparent. So we are allowed to use the I pointer to point to the int, but we're not allowed to use the float pointer because it points to a float object. But we have no float object. We've destroyed the float object. And laundering doesn't help us because we still don't have a float object. Right? There is no float object we can dereference. We're only having an int. So this is still undefined behavior. So std launder exists. When do you need to use it? When you want to reuse the storage of const heap objects, because remember, you can't use the storage of const non-heap objects. When you want to reuse the storage of base classes or no unique address members. So in other words, never. We're going to get back to that. And also note that when launder was originally introduced, the rules were more strict about transparent replacement, and there were more situations where you'd have to use launder. Essentially, generic code always had to use launder, but this was annoying, so the rules were relaxed. And now, essentially, launder is never used. Again, we're going to get back to that. So at this point, it's going to start interesting. So questions about placement new and object reusing. Are you still following me? Okay. Then just jump right into the deep end and talk about implicit object creation. Now, we've got another tautology. An object is created by an operation that implicitly creates objects. Thank you. What's the motivation behind that? Consider this C++ version of C code. We call std malloc to allocate storage for an int, and then we just start using it as an int. According to all the rules I've described so far, this should be undefined behavior, because we don't have an int object anywhere. Nothing has created an int object, so how can we just start writing to one? Who created that for us? But it really shouldn't be undefined behavior, because that's the way you did it in C, and it should just continue to work. But for like 22 years, until C++20, this was undefined behavior. Nobody, like everybody did it, but it was undefined behavior. And this was just a bug in the way object creation and lifetime was specified. Because as I told in the beginning, like this is an invented property the standard talks about semantics. It has no effect on the actual runtime behavior of your code, right? Unless the compiler decides to optimize. So this was a bug in the specification. This got fixed by saying, okay, some operation implicitly create objects. And spoiler alert, malloc is one of them. So those operations, essentially, the compiler is doing something unique. When you've got implicit lifetime types, like int, the compiler will implicitly create and start the lifetime of objects if doing so would prevent undefined behavior, which is pretty nice. So if it helps you to prevent undefined behavior, the compiler will just jump in and catch you and say, you're about to do undefined behavior, let me fix that for you. Which is like the only instance of the C++ standard where the compiler does that. In all other instances, it goes, oh, you have undefined behavior, let me just do something entirely different. But like here, it actually goes ahead and helps you. So the caveat about the implicit lifetime types is just pretty obvious. Like if you've got a class whose constructor and destructor does something, the compiler will not implicitly call those, because then this could just silently allocate memory or whatever, and you don't want that. So this only applies to types where the constructor and the destructor do nothing. But this is enough to fix the code where we got like C-like code that just calls malloc. So which operations do that? Well, for example, malloc and variance operate a new, allocator, allocate, and a bunch of other allocation functions. So the compiler looks at this code, looks at the second line, where we're using an int object that doesn't exist, and because malloc can implicitly create an object, the compiler goes ahead and says, you know what, let me just create an int for you. So to make this code well-defined, which is nice. So we've accomplished the goal of having like C-like code is still valid because the compiler implicitly creates an int object without you having to do anything. Anything that starts the lifetime of an unsigned char or stored byte array also creates objects. So here we've got a buffer for an int, and then we start using it as an int. We haven't created any int in there, so the compiler helpfully went ahead and creates an int to make this code valid. Except that's the idea. There's actually another bug in the standard here, where we have to use a std launder. I don't want to go into why we need the std launder in there right now. Just pretend it doesn't exist, and it really shouldn't be. It's a bug in the standard, but for now we have to write the std launder in order to get the pointer. But ignore that. The idea is we've got some buffer of unsigned char. We use it as an int, so we can just start. The compiler creates an int, and we can start using it. Memcopy and memmove also implicitly create objects. So here we've got a char buffer. A char buffer is not an unsigned char buffer, so it doesn't apply the previous exception. But when we memcopy an int into it, the compiler implicitly creates an int in the destination, so we can start using it as an int. And again, we need to use this .launder for the same reason as on the previous slide, just pretend that isn't there. So this code is fine because the compiler implicitly created an int for us, even though we didn't do anything. And then the implementation can let implementation-defined operations, probably mmap, virtual alloc. So when you want to read just map some memory where you know your data structure is in there, you can just cast the pointer to that type and start using it, even though you formally haven't created any objects. And before C++20, such code would have been undefined behavior, because you just started using it as if there were some objects, even though there weren't any. But now the compiler will implicitly create an int object in order to make this code valid. Now, while this is certainly useful, it's also pretty bizarre, because for starters, it uses time travel. So in this code, we've got a buffer that can fit both an int and a float. And then we roll a dice, and depending on the dice roll, we either use it as an int or as a float. Now, it's important that the reinterpret cast doesn't do anything. It doesn't create any objects. It's the first line that created an object. So when we, for example, want to use it as an int, the compiler has to travel back in time in order to create an int at this point. Alternatively, you can say it's quantum mechanics, and when we create the buffer, we simultaneously create an int or a float, and then when we use it as one, it collapses, and we have always created an int or float. But in either case, it's like pretty bizarre semantics. And also note that once we've put an int in there, when we start using it, it always is an int. We can't just silently start using it as a float later on. That would be undefined behavior. The compiler implicitly created an int, and now the choice is stuck. And this sort of time travel semantics is only possible because, again, for the CPU doesn't care. It's not something that executes on actual hardware, it's just some semantic fix for the standard. And again, the launder is necessary because of the thing I will get to later. And just like std launder, implicit object creations is not a magic thing that prevents all undefined behavior. So when we use code like this, where we got our int and we reinterpret cast to a float pointer, the compiler will not create a float for you. So this is still undefined behavior because we are dereferencing a float object, but we don't have a float object. We just have an int object. Sure.
Sorry.
Hi.
Tool to reveal when your compiler creates objects for you, something you could actually see.
Yeah, so is there, no, but it's just the situations I've listed implicitly create objects. And some implementation-defined functions which also allocate memory will also do that for you. But it's also, it doesn't really, you don't really need to have it revealed because by definition it doesn't do anything. Right? It only applies to implicit lifetime types because otherwise you would get in trouble with actual time travel, which isn't implementable, I think. So this is all good, but consider a code like this. So we've got a process, we get some buffer. And then we want to start using it as an int. This might be undefined behavior, depending on how we get the buffer. Like if it's from one of those magic places where the compiler will time travel back to and create the int, we're good, but we don't know that because it's just a function. So we want to make sure, okay, please always get me an int there, even if we're in one of the situations where we wouldn't have gotten an int otherwise. And you might be tempted to say, okay, we do placement new. So we placement new inside the buffer an int, and now we've got an int. While this is well defined, we might not get the same value. Because even though the placement new for the int the initialization doesn't change anything. Physically, semantically, it changes it. Semantically, it creates an entirely new object that has nothing to do with whatever was there before. And so we don't have any guarantee that this is a no-op and doesn't physically change the bytes. So even though this is well defined, we might have 11 in there, and now we might have something entirely different in there because placement new changes if we've created a new object, we've lost the property. What we want, yes? No, I don't see a C-style cast. So we static casting and now the placement new at the end, placement new of an int returns an int star. So this always has the correct type, and then we're casting an unsigned char pointer to a void star, but this is a static cast. Yeah. Yeah, so yes, this function assumes that there's an int in there. But it's also fine because we're explicitly creating a new int, right? This just gets some memory, it assumes it's big enough and creates an int in there. This doesn't read the existing bytes interpreted as an int, which is what we actually wanted to do here. So what we want to do is we want to say, okay, we've got this buffer, let me create an int in there, but please don't physically touch the bytes. And for that we can use start lifetime as. This takes a pointer and a type, and it will return you a pointer to an int in this case, whose lifetime has started. So now we're taking arbitrary bytes, and we're starting the lifetime of an int object in there, and read whatever the byte values were interpreted as an int. And this is well-defined behavior. So when you want to write code, for example, you're doing socket IO, and you've got some bytes from the socket, and you want to say, okay, the other side sent me this data structure. You can use start lifetime s with your data structure and say, this is my data structure, it now lives in the bytes of the socket. And you've got completely well-defined behavior. There's also a version for arrays, which takes like a dynamic count. And yes? Sorry, there's a microphone coming.
What's the difference between start lifetime as versus reinterpret cast?
So the reinterpret cast is undefined behavior, potentially.
In all cases?
No. So if you've got an int object, you reinterpret cast to unsigned char, and then you reinterpret cast it back, that is fine. But if you've got something that isn't an int object, then it's undefined behavior because you're using an int object without one that has been created. And start lifetime as always creates an int object for you. So this code is always well-defined. It doesn't matter what lived in buffer before.
So if there was a float in the buffer and
so if there's a float in the buffer, you will then reinterpret cast the float as an int, but without undefined behavior. I will get back specifically to the float int example later on when we talk about type panning.
Thank you.
But this is just code. You, for example, like as I said, you've got bytes from the socket coming in. You know this contains some data structure. You start the lifetime of that data structure, and then you can just use it directly. Yeah.
But like, so let's assume I have like a float pointer and I like give it to this function. And like there's a float happily living in there, and now it's like start lifetime as int.
Yes.
And then I return. Like, is my float now broken?
I'm going to talk about that when we talk about type panning. For now, in this case, assume that we just got bytes, and we want to read those bytes as an int. Because they come from network, they come from file mapping. Then you can use start lifetime as to get well-defined behavior and start reading them as an int without having to touch them. Okay, sure.
In all your previous examples, you've deliberately aligned the storage beforehand, but here, what's the alignment of buffer? And could it be wrong?
Yes, so this code assumes that the buffer is big enough to hold an int and is properly aligned for an int. Otherwise, you will still have undefined behavior for the other reasons, yes. Okay. Now, start lifetime as, just like launder, is a magic standard library function. But we can actually implement it, sort of. So this is a potential implementation of start lifetime as. We do a memmove of pointer to pointer of size of t bytes. So this is a now-up, like it doesn't move any bytes because source and destination are the same. But remember, memmove implicitly creates objects for you. So when we return then a pointer to t, which we might have to launder because we don't know where it came from, and then later use it as a t, the compiler will travel back in time to the memmove and create our t object in there. So that way we get the implicit creation of the object without having to do anything. The standard library implementation is an actual no-op, it's just a compiler intrinsic, and it also works for const. This one doesn't like const. But essentially we can delegate to the memmove thing. This isn't useful to know, it's just cool. So we've got implicit creation of objects. There's also the flip side, implicit destruction of object. Because even though we can call destroy to explicitly create an object, the mere act of releasing storage or reusing storage also destroys objects. So in this code, we don't need the destroy for the x. Because just the act of calling placement new ends the lifetime of whatever was in there and starts the lifetime of a new thing. Similarly, when we've got our unsigned char buffer, this starts the lifetime of an unsigned char array. And when we call placement new on there, this ends the lifetime of this unsigned char array and instead starts the lifetime of an int. And then we can use that pointer. And we also can't use the buffer anymore as is, because we don't have an unsigned char array anymore. We just have an int object. And because the lifetime of an object ends just by releasing the storage or reusing the storage, this means that memory leaks are not undefined behavior. So here we've got a std string, we placement new a new string in there. This ends the lifetime of that string object, but it doesn't call the destructor. So we've got a memory leak, but this is perfectly fine. This isn't undefined behavior, it's just a memory leak. And then we use it. And again, we will destroy the string object, but this will destroy the new string because we've got transfer and replacement. So we've got some situations where we implicitly create objects. We can use start lifetime s to explicitly create objects, and we can implicitly destroy objects just by reusing the memory. Any further questions about this part? Okay. So let's talk about provenance. Consider this code. We've got two int objects, x and y. Y is 11. Then we do something with the address of x, and then we return y. We expect our compiler to optimize that return y to return 11, because y is 11 and nothing changes y. But what if do something does this? So do something takes the pointer, gets one further, and sets this to 42. And it might just happen that whatever this address is the address of y. So now we're changing y in this function, so the optimization is broken, right? Well, no, because we don't know that this could be some arbitrary address. So let's say we do that. If the address of x plus 1 is the address of y, we call do something. And do something modifies whatever is stored as address of x plus 1, sets this to 42, and we know that this is the address of y. So this sets y to 42, right? Which means that the return 11 optimization is definitely broken. Because if we reach this condition, y has been set to 42 by this code. Because that's the address of y that we're setting here, right? Except the optimization is still valid. Just because two pointers are equal, just because they point to the same address, doesn't mean they point to the same object. They're not interchangeable. I'm going to say that again. Just because two pointers are equal doesn't mean they point to the same thing. This is because a pointer is two things. We've got the address. This is the physical thing. This is what's being compared. And it's got something called provenance. And the provenance identifies the object or location the pointer came from originally. And the pointer dereference is only valid if the address is in the allowed range of that allocation as determined by the provenance, and the current provenance of that address still matches the provenance of the pointer. And crucially, pointer arithmetic doesn't change provenance. So let's look at the example again. So the comparison x plus 1 and the address of y, this compares the addresses. Even if this returns true, the provenance of pointer plus 1 isn't the same as the provenance of the pointer to y. So we can't dereference it because it points to memory location, the address isn't in range of the allowed provenance. So pointer has a provenance address of x, and that provenance doesn't allow dereference of pointer plus 1 because it's the invalid address range. So this is still undefined behavior. Even though it has the same address as another object we could modify, we're not allowed to do it via this pointer. And this is crucial for the compiler to optimize that to return 11. Because it sees that the address of y isn't, nobody does anything with the address of y. Nobody can change it. Because the only way to get a pointer to y is via taking the address of it. We can't do pointer arithmetic to randomly get it. And similarly, we can't do like reinterpret cast u and pointer some number to get y, because that would have the wrong provenance. And this is also related to launder. So here we've got our const int object allocated on the heap. This has provenance A. We then destroy it. We then create a new object. Because we're having non-transparent replacement, this has provenance B. So when we use new pointer, it has the correct provenance for that address. But when we use pointer, it has the wrong provenance. It still has provenance A, but the object has provenance B. So this dereferences undefined behavior. We have to launder it. Because what launder does, it takes the address and fixes the provenance. It keeps the address unchanged, but sets the provenance to B. Because that is the currently valid provenance of that address, and then we can use it. And the same thing also applies to references. So reference also has provenance. It has the provenance of the A object, so when we replace it, the provenance is wrong, so we have to launder it. So provenance explains to launder. Every object has a unique provenance, except when it's in an array, then they all share the same, so you can use pointer arithmetic within an array. And reusing the memory of an object changes it if you don't have transparent replacement. And if you use .launder, you can update the provenance of an object. Questions about provenance? So it's a bit of, yes?
Sorry. In the very first example where you said dereferencing p+1 is ub, how does the compiler figure out if that pointer is just an integer pointer or pointer to an array?
So how does the pointer figure it out? The compiler doesn't need to figure it out. So the compiler, the function do something is fine on its own, because this might be called with an array and then it's fine. It's when we call it with the address of x, do we trigger the undefined behavior. And so the compiler looks at both functions in isolation. It sees, okay, this one we're just doing a store, this could be an array, this could be fine. And when we look at this function, the compiler sees, okay, we've got y, we set y to 11. Then we take the address here, but we don't do anything with it. And then we're just doing something with x, which is all good. Because of provenance, this can never modify y. So we can optimize this to return 11. And at runtime, we trigger undefined behavior, but this isn't only detected when we see both functions in isolation together. When we see them in isolation, both code is fine.
Thank you.
Because again, like provenance is all, purely a semantic thing for the standard. Like it doesn't, it's not in hardware. Oh, that was the wrong direction. Okay. So with that in mind, we can look at type panning. So we are assuming for the remainder of this section, int and float are the same storage as before. We've got an int object, we create a pointer to it. This is fine. Then we've got a float, then we reinterpret cast that pointer to float. That one is also fine. The problem is the last line where we dereference the float pointer. And this is something to do with strict aliasing. And colloquially, we'd say that, okay, you can't reinterpret cast between unrelated types. But more this is wrong. We can do the reinterpret cast. What we can't do is the access. So if a program attempts to access an object to an L value of a type that is not similar to the type of the object, we have undefined behavior. So you can't access an object to a pointer of a type. In the previous slide, we've got an int object. We're accessing it to a pointer to float. This violates this rule. But merely having the pointer is fine. The type of a pointer or reference is irrelevant until we access it. We can freely reinterpret cast between pointers as long as we want, but as soon as we dereferencing, they need to have the correct type. Otherwise, the type is entirely irrelevant. So this brings me to this code. Somebody alluded to that, not quite, but similar. So we've got our int object, we put a float in there, we've got a pointer to that float, we can use that float. This is fine. We can't use I anymore, because this is non-transparent replacement. We don't have an int object, we have a float object. We can't access an int object, a float object via an int object. This violates strict aliasing. This is undefined behavior. Similarly, this is what somebody mentioned earlier. So we can do start lifetime as float on the int object. Then we got a pointer to a float that happens to have the same bytes as the int, and we can use it. But we can no longer use the int. We've ended the lifetime of that int object by replacing it with a new one. So as soon as we do start lifetime s, the original object at that address ends, and we can no longer use it. So if you want to do some bit of type punning, right, and don't care about the original one, you can use start lifetime s. It's a bit weird, but it's fine. Like there's no undefined behavior. Yes.
Could I use start lifetime as a second time with the int, or with the float to get the int back?
Yes.
Would that be possible?
Yeah, you can use.
So
I don't think so. So if you do like a start lifetime s.
So on the f pointer, like on the.
Yeah. If you do start left as the f pointer.
As an int.
I don't think I itself is valid again.
Okay.
Because we did a non-transparent replacement and then another non-transparent replacement. And I don't think this tracks through that.
Yeah.
But what you can do is launder I, and then you can start using it again.
Ah, okay.
Right?
Yeah.
It's just the provenance itself that has changed. Right? So we've got provenance A for the int, then we've got provenance B for the float. When we create the ints back, we got provenance C, right? And so we can no longer use the name. But in principle, it's pretty weird way to do type panning, but like it would be fine. I mean, this is essentially what I mentioned. So we've got our float pointer here already. Then we do the placement new. That float pointer is wrong. Even though it has the correct address, it has the wrong provenance. It has the provenance of the int object. So we cannot access it directly because it has the wrong provenance, right? And again, like this is weird if we don't know provenance, because we've got a pointer to the correct type. It points to the correct address, and we have an object of that type at that address, but we can't dereference the pointer because we got it the wrong way. And it doesn't help if you do it in this order, right? We still got a pointer that points to a now destroyed int object, so we can't use it because it still has the provenance of the old int object. We have to either use the pointer we get from placement new, which gets the correct provenance, or we have to launder it. This is like really subtle, but I hope it makes sense. And this brings me to the bug in the standard. This also applies to unsigned char, which is really unfortunate. So here we've got the unsigned char buffer, and then we reinterpret cast as an int pointer. And even though the compiler would happily create an int object in that buffer for us to make it valid, we don't have a pointer to that int object. We have a pointer to the unsigned char object of the wrong type. So this is undefined behavior because we are just having a weird pointer to an unsigned char object, not a pointer to an int object. And this is just a bug in the standard. Like there is some wording in there that says that this pointer has the same provenance as any object created inside the thing, which this paper adds, but until that wording is added, we have to use launder. And again, like this is a spec bug. Like this should work because otherwise the entire rule doesn't make sense for the implicit object creation here. So this is the final situation where you might want to use launder. When you want to reuse memory as storage for a different type, you have to launder it. Especially with unsigned char, but that's going to be fixed hopefully. So never use launder, but terms and conditions may apply. So there are two exceptions for the strict aliasing rule. The first is we can always access a signed or unsigned version. So when we got our int, we can exit this as an unsigned int. Even though we don't have an unsigned int anywhere, we can do that, which is nice, I guess. I don't know. The second one is more interesting. We can exit this as a char, unsigned char, or std byte. Now the idea here is that, remember, an object occupies storage, which is just a sequence of bits, and we want to print those bits as bytes. So we can iterate over it as a std byte and print out each individual byte of the object. This is why the reinterpret cast exception exists. Unfortunately, there's another bug in the specification, which makes this entire code undefined behavior. Because we're doing pointer arithmetic, but we don't have an array of bytes anywhere. So we can't do pointer arithmetic. And like this code's meant to be valid. It was valid in the past, but it got fixed by, got broken by a drive-by change to something else. And there's another paper to address this. They're just trying to figure out the wording to make this valid again. So, you know, you're like pretty deep when you find bugs in the C++ standards for this sort of rules. So more explicitly, to sum up, we can do type hunting with std lifetime s. The reinterpret cast is undefined behavior because we don't have a float object, but when we create a float object, we're good. But we can't use I, because we don't have I anymore. Like we don't have an int, we've got a float. The other famous way to do type hunting is via union, and this does not work because of the final phrase in that sentence: an object is created when implicitly changing the active member of a union. So we've got a union of int and float. We create an int, we create a float. This changes, creates a new object, destroy at the same address as the int, so we destroy the int object. So we've got a float anymore, but no int. This is undefined behavior because we're accessing an int object that has been destroyed by reusing the storage by assigning it. There's one exception. So when we got two standard layout structs in a union, and they both start with the same list of members, we can access those members that are common in both variants from either member. It doesn't matter what the active one is. So here we've got a union with A and B. Both A and B start with an int. This is in the common initial sequence. And then it doesn't matter whether we write u.a.prefix or u.b.prefix, because both have prefix, right? We can just access it however we want. Now, this is not related to lifetime. We're not changing the lifetimes of anything. It's as the second line u.b.prefix, it's as if we have written u.a.prefix. The compiler will just automatically change it to whatever is the correct member access to make it valid. So this is just a convenient rewrite rule that we're getting at runtime. This has nothing to do with object lifetime, but it's pretty convenient. So for example, when you have a tag union, you can put the tag inside each struct variant as the first thing, and then you can access it directly and save a bit of alignment in some situations. We can do type hunting via std_memcopy. And again, this is because we've got an int object and we've got a float object, and we're just copying the bytes over. Right? It's non-controversial. We've got a float, we've got an int. We just transferred the bytes. No lifetime business is going on here. The more modern way is to use bitcast. So bitcast is essentially a const by memcopy that just works. Yes? Yes, the size is the same. I did a static assert a couple slides ago that still applies here. Yeah. Yeah. Now there's one final exception where type hunting also works. If we've got a standard layout struct with one or more members, we can do the following. So we create our struct object, and then we create a pointer to the first object by reinterpret casting the A, the struct object. This is always fine because we can always reinterpret cast. But we're also allowed to dereference that pointer. Even though that pointer points to an A object and not to an int object, because the A object starts with an int object, we are allowed to access it. And we can even go the other way back and reinterpret cast the pointer to the first member back to the parent struct and access it. Yeah.
Hi. In terms of the standard then, and the concept of being transparently replaceable, if you have a base class, which you can convert to a derived class, is that technically transparently replaceable, or is that a workaround?
No, because the transparent replacement exception was you can't do base classes. Okay. Because then you get into vtable business and stuff like that.
Okay, sure, right. Thanks.
Yeah. So this works because there's a special exception, the pointer interconvertible exception. So if two objects are pointer interconvertible, then they have the same address, and you can obtain a pointer to one from the other via reinterpret cast, which means that essentially the address of A and the address of A.member have the same provenance, so we can just get a pointer through one to either one, and it doesn't matter. And it applies to the same object, obviously, but also unions and their members, and standard layout structs and their first member. and then it's transitive. And the fix for the unsigned char buffer stood launder reinterpret cast would also add like another condition to say that an unsigned char buffer and any objects created within it are pointer interconvertible to make the reinterpret cast work. But it's currently missing the wording, so it's still undefined behavior. Yes?
I don't know if you're covering this in following slides, but does this also apply to enum classes with regards to their underlying types?
No, this does not apply to enum classes and the underlying types. This is the full wording for the pointer. Yes. So let's end this talk by talking about invalid and zombie pointers. So access of an object outside its lifetime. So before the lifetime of an object has started, or after the lifetime is ended, any pointer can only be used in limited ways. Similarly, any reference or the name of the object can only be used in limited ways. Essentially, there's like a bunch of wording that follows, but essentially, you're fine to use pointers, but you can't dereference them, which makes sense. So for example, we've got our X object be destroyed. We can form a pointer to it. We can even form a reference to it. We can form another pointer from that reference, or we can form a reference from that pointer. This is all valid because we don't access the object anything. We're just creating different names and different pointers of it. And then we can also compare the pointers. Pointers have to be equal. This is all valid, even though we don't have an object anymore, we're not accessing it. But as soon as we access it, we've got undefined behavior. So we read the value. We dereference the pointer. This is obviously undefined behavior because we don't have an int anymore. So we've got undefined behavior when we use such a pointer or reference to access the value, to read its value, to write its value. To call a non-static member function, to delete it, or to do anything with virtual base classes or dynamic cast. Then the object has to be alive. Which seems pretty intuitive, right? You can compare the addresses of the destroyed objects, you just can't dereference them. This makes sense. Now there's one important exception here. This will only apply after the storage has been allocated and before the storage has been deallocated. Because if you access a pointer to something that hasn't been allocated anymore, now things are going to get interesting. So this is colloquially called the pointer lifetime end zap. So when we reach the end of the storage duration, all pointers that have addresses inside that storage duration become invalid pointer values. Indirection of them, so dereferencing, is undefined behavior, and any other use is implementation defined, which can include traps. What this means is that in this case, we've got our int objects on the stack, we create a pointer to it, we destroy it. We can obviously no longer dereferencing pointer, but we can still compare it, right? It's not going to be null pointer. But when we've got an object on the heap and we delete it, now pointer points to deallocated memory, which means that the compares to null pointer is actually implementation defined, which means the compiler can insert a std abort here when we compare a pointer, which is very interesting. So why does this happen? Well, it's again compiler optimization. The compiler would really like to assume that every time you call new, you get a brand new pointer that the world has never seen before. This makes alias analyzing a lot easier, because you don't have to worry about the allocator reusing storage. But the allocator is obviously going to reuse storage. So we just make the comparison implementation defined, so you can't really observe that in the standard confirming program. In principle, we could also do some safety stuff. For example, we could have delete of a pointer, can set it to null. This would be a valid implementation, because the comparison with null pointer is implementation defined. Similarly, when we've got a function that returns like a pointer to its stack memory, which would then be deallocated by the time we get the pointer, this could also become null pointer. So when you write return local address, this could be translated into return null pointer for safety reasons. No implementation does it, but it would be allowed. Now, this behavior of invalid pointers has pretty interesting consequences when we consider multi-threading. So this is an example I've taken from a paper. We've got a stack, a multi-threaded stack. So we've got a singly linked list of nodes, and each node has a next pointer. And then we've got a push function, which gets the current top, sets the node next pointer to the current top, and then we're doing compare exchange loop until we finally manage to correctly set it. So if while the time between getting the top and setting it, some other thread could have changed the top, in which case we have to try again until we correctly set the correct thing. And then we've got pop all, which simply sets top to null and returns the entire list to some thread to do whatever it wants with it. Now, we can imagine the following execution. So we've got our list containing of a single node, node 1 at address A. Then we've got one thread. One thread allocates node 2. It has address B. It executes old top equals top and sets new node next to old top. So now we've got old top pointing to node 1 and node 2 also pointing to node 1. All good. But unfortunately, now another thread comes in. This thread executes pop all and deallocates node 1. So now old top and node 2 point to deallocated memory. Which means that when thread T1 does the compare exchange weak, the result is implementation defined. Because old top is an implementation defined value. Deallocated memory, this may or may not succeed, or trap, or do whatever. And as long as the implementation defines it. Which is bad. But it gets even worse. Consider we're in this situation. There are 2 deleted node 1. It now allocates another node, which happens to reuse the same memory and successfully pushes it. So node top points to node 3, and old top points to node 1, and node 2 next points to node 1. Then the compare exchange weak is also implementation defined, because old top points to deallocated memory, logically. It has the wrong provenance for the different top. And like, what can the comparison do here? Because if the comparison says it returns true, they have the same addresses. We've got the wrong provenance in there. Node 2 next has the provenance of node 1. So if the comparison returns 2, any access over the list will be undefined behavior because we're not allowed to dereference it node 2 next's pointer. It points to the wrong thing. Even though it has the correct address, it has the wrong provenance. So the comparison has to return false. But that's not implementable because the provenance isn't stored in the pointer. This is just a one-time property. So nobody can correctly compare the provenances in there. So whatever we do, it's sort of screwed here, right? Yeah, and this is a bug in the C++ standard. There is lively debate about how to solve this one. Because on a hardware level, it doesn't matter at all. Because on the hardware level, none of this provenance in invalid pointer values has any effect. But like in the specification, it has an effect. And according to the specification, we can't write this code. Now, the solution from the paper, if you're taking the example from, is to say, okay, comparison with invalid pointer values is meaningful, it does what you expect. Implementation isn't allowed to silently change those bits. And then we need to use some sort of launder mechanism to automatically update the provenance of not just the pointer, but every pointer reachable from that pointer. And this is a bit bad for optimizations because as soon as one of those functions exists, the compiler can't do a lot of optimizations anymore because it has to assume that this function gets called all the time in code it can't see. Right? So this isn't ideal. And yeah, like that's a bug in the C++ standard. It's just purely the wording doesn't allow this sort of behavior. And on that note, I end this talk. So some personal guidelines. Don't rely on implicit object creation, right? While nice, it's weird. Like we've got the time travel behavior, it's non-obvious when this happens. Just use placement new to explicitly create an object. Like this makes it clear we're creating a new object here, we don't care about the previous values. When you do care about the previous values, use std start lifetime s. So you mmap your memory that contains your data structure, call std start lifetime s to get a pointer to that data structure, and just start using it. Right? It makes your code more expressive to use. Whenever possible, use the pointer from placement new and start lifetime s directly. Because that pointer is guaranteed to have the correct provenance. Then you don't have to worry about the transparent replacement rules. You don't have to call std launder. Right? Just use the pointer they give you. In some cases, this isn't really possible because it would mean storing an extra pointer in your std vector, for example, because you need the correct pointer, even though it has the same bits as the other one, then use std launder. It inhibits compile optimization, but otherwise it does nothing. So it's fine to also call std launder in cases where you don't need to. It's going to be fine. And instead of an unsigned char buffer, use a union, right? So for example, stored optional, either needs to hold a T or nothing. You can implement it using a union or an unsigned char buffer, but the unsigned char buffer, you get into troubles with the bug in the standard. You might have to use .launder again. It's also not const expert, so just use a union of a char that's empty and a T, and then you follow the more type-safe rules, and it makes it easier. Like, all of those details about implicit object creations are kind of nice, but we've got this explicit functions. And like, I think C++ would be a better language if we didn't have to worry about whatever the implicit semantics we got to support C code were, and we just have explicit syntax to create objects, start the lifetime, not create the objects, and so on. And with that, I'm done. So I work at ThinkCell, as you can tell from the logo. We're also hiring. So if you're looking for a job, we're hiring. I've got a bunch of merch. Like I've got socks and raincoats I can hand out afterwards. I'm blogging now at the ThinkCell developer blog. So if you know my blog before. The slides will be available at that URL. The website doesn't exist yet. I will create it. So if you're watching this on YouTube, you can go to that URL. Otherwise, don't. Thank you very much.